Sorry. No, I made some of that very
Thank you.
Mirth really is.
Young man.
That's true.
Good morning, everyone. So we're just going to continue from where we stopped yesterday. And we have a lot to do today because we must complete everything that needs to be done on chemical kinetics today. So, good morning. I'll just advise that there will be time for questions because I consider that very important. So don't worry. If you have any questions, just note them down. Then, like I said, we'll finish chemical kinetics quickly, then we can go to chemical equilibrium. Now, okay, so we were on type of rate laws yesterday, we said there's a rate, of course, we discussed rate laws extensively yesterday. And we also said that there are two types of rate law. You have the differential rate law, which tells you how rate of a reaction depends on concentration. And that's what we have been discussing so far. We've not spoken about integrated rate law at all. So we've not spoken about, you realize that that equation contains rate and concentration. If you look at everything we've written in terms of rate law, it's just, this is an example. You have rate, you have concentration. And we just said that differential rate law shows you how how rate depend on concentration. But there's a second one, which is the integrated rate law, which shows how concentrations depends on time. It shows how concentration depends on time, meaning that essentially what you're going to be having in an integrated rate law, you won't have rate in integrated rate law. What you're going to have, because if you look at this, you realize that we don't have time in this. We only have rate and concentration. But mind you, you will know, I'm sure you know that within that rate that you're seeing, there's also time within that rate. There's also time within that rate, but it doesn't show in your equation. What you just see is just rate concentration, meaning that anytime you have a concentration rate data and you want to determine anything with concentration rate data, that means you're going to be using the differential rate law, because that's what you have. You don't have any information to do anything else. The information you have can only be interrogated using the differential rate law, because it's the one that contains rate and concentration. While the integrated rate law, you will have concentration and time data. We'll see examples of that. But again, integrated rate law comes from differential rate law. Integrated rate law, they are as a result of the integration of the differential rate law. So it's not like they are two separate equations. One is an outcome of the other. Integrated rate law is as a result of the integration of the differential. So when you integrate the differential rate law, you get the integrated rate law. In the course of that differentiation, rate disappears. You will end up, because there's a way it's broken down, because you're going to have to break down your rate also. So you end up with concentration time data. So now this is an example for a zero order reaction. Remember, we said zero order reaction rate doesn't change with respect to concentration. Concentration remains the same. Rate remains the same throughout the course of a zero order reaction. Now, you have an example, you have A to give you product. When it is a zero order reaction, then the differential rate law is going to be equal to, now remember I told you that differential rate law is also, integrated rate law is as a result of the differential, comes as a result of the differential rate law. Now, if you look at what you have now, normally if you want to write this, your rate, because if you look at what we have rate is equal to, if you want to write this as just your differential rate law, the original one, really, your rate is going to be equal to your K, concentration of A raised to power 0. That is the differential rate law we're coming from. But now, you now want to break down that rate. You are not just going to be writing rate. You want to break down the rate. And remember, by convention, what we've always spoken about is that rate is the rate of change of concentration with time. Rate is the rate of change of concentration with time. Now, and that's why you have your rate is equal to minus dA dt. That is breaking down that rate into change in concentration of A divided by change in time, which is the definition of rate we have spoken about. Now, rate is going to be completely out of this equation. Rate, that R is going to be completely out of this equation. You end up with your dA minus dA dt, which is equal to K concentration of A raised to power 0. If it was the first order reaction, rather than having that 0, you will have 1. But we're saying that it's a zero order reaction. That's why you're going to have 0 there. Now, like I said, your integrated rate law comes as a result of integration of your differential rate law. Now, you now go ahead and integrate without the R now. The R is completely out of this equation. What you just need is your minus dA dt. Now, again, why do we have minus in that dA dt? Where is that minus coming from? Now, we have the minus there simply because, remember, in the course of your reaction, concentration is going to decrease. Because we have decreasing concentration, that's why you have a negative there. It's signifying a decreasing concentration because we're using the reactant. If we're using the product, that means that there's not going to be any negative there because the product will be increasing with time. But in this case now, we're using the reactant and we're going to be using the reactant. Forget about the product completely. But by convention, concentration, not even by, it makes sense that the concentration of reactant decreases with time, and that's why that is carrying a negative, and that negative is very important. So the integral now becomes, you can now rewrite the integral to be equal to, like I said, you're going to be integrating. You are rewriting that equation as dA, so that's minus dt, so you've done cross multiplication, so you've multiplied both sides with dt, so you end up with your integral dA dt, k dt, so you apply your integral now. So now if you do that integration, you end up with your AT is equal to minus KT. Now, this is the integrated equation for a zero order reaction. Now, what is the graph telling us? What is this graph telling us? Now, for a zero order reaction, if you want to know whether a reaction is a zero order reaction, all you need to do. But again, for a zero order reaction, the rate will remain constant anyway, because the fact that the rate is not changing, that is how you know that a reaction is a zero order reaction. Now, but if you just want to use your integrated rate equation to determine whether a reaction is a zero order reaction, remember that you'll have a table, like I said, integrated rate law relates concentration with time for any reaction. But now, so that means if anybody gives you a concentration time data for differential equation is going to be, that means you're going to be using rate concentration data for differential equation. But anytime you have a concentration time data, more often than not, you're going to be using integrated rate law to interrogate your reaction. Now, in this situation where you have concentration time, so if you have a table where somebody gives you concentration and time for a reaction, they give you concentration at time 1, concentration at time 2, concentration at time 3, concentration at time 4, and they write the time there. So all you need to do is just plot that concentration against the time. When you plot the concentration against the time, if you have a straight line of this nature, what that tells you is that that reaction is a zero order equation. If you don't have a straight line, it means it's not a zero order. But if you have a straight line like this, then the rate constant is going to be the slope of that straight line. Now, what does this straight line mean? That straight line, what it's telling you is that when you plot concentration against time, the rate does not change. Because if the rate was changing, you won't have a straight line, you'll have a curve. You will have a curve, because that means at every point on that line, because if you want to determine the rate at any point, you draw a tangent around that straight line. Now, when you draw a tangent, you use the tangent to calculate the slope, and the slope is the rate constant, and the rate constant should be the same. Now, if you now do this, and again, in this case, we're not having any complicated equation. So, but what this straight line is telling you is that the concentration remains the same throughout that reaction. The rate remains the same, not concentration. The rate remains the same throughout, and that is the definition of a zero order reaction. Now, for a first order reaction, if the reaction is first order, now remember that, so that we don't get confused, we already did, remember we looked into this method of determining order of reaction and writing your rate law. Now, while we were doing that, we used this method because we were given concentration rate data. We were given concentration rate data. So that's why we use the differential rate law because we had concentration rate data. But now, so that you don't be like, oh, which one do we use? How do we know which one to use? I know that a lot of people a lot of you are not listening. And I can bet you that some people will still come up with that question. Why are we using, when do we know how to use it? Now we use that where the kind of data you're given determine the method you're going to use. So when you're given concentration rate data, that means you're going to resort to that differential method. But when you're given the concentration time data, that means you're going to be using the integrated rate law to interrogate your information, to interrogate your data. Now, in this case now, we're saying that, okay, this is a first order reaction. Your differential rate law is going to be this. From what we said about the zero order rate law, you can see that your R is equal to Ka raised to power 1 because it's the first order. Now you break down the R. When you break down that R becomes minus dA dt, because that means the change in concentration of A with time. And I already told you the reason why we have a negative there. The negative is there because the concentration of A is decreasing over time. Now, you now do the integral. You rearrange really. In this case now, you multiply both sides by the T, and you also multiply, you multiply both sides by the T, you also divide both sides by A. So you will end up with this next equation that you now integrate. When you integrate that equation, what are you going to have? Okay, sorry. Okay. Why? Okay, something is missing here. The final equation is missing. Okay. Okay. So the final equation, so that I don't lose you. So your final equation is because there's a table that gives you the final equation. So I just wanted us to quickly come here. For a first order equation, that means, of course, your final equation is just going to be because that last equation that is missing on that table is going to be your ln 80. Where is it now? So that means here, the equation that is missing is going to be ln 80 is equal to ln A naught minus KT. Ln 80 is equal to ln A naught minus KT. So that is missing here. So I'm going to try to please, though it's in the table. We already have it in the table. Anyway, I already sent this material to you. I didn't know that was missing. So now, what does that mean? I need to really come back and explain what that means also. And now you can see that you have this equation. So you also have this graph. So what is the work of this graph? Now, what this graph is telling you is that when you have, remember, I just told you that if you have concentration time data and you want to determine the order, if you try plotting, you use the integrated rate equation for zero order. If you get a straight line, that means it's a zero order. If you don't get a straight line, it's a curve. That means it's not a zero order, but you still need to test which one is it. Is it first order? Is it second order? So now, if you now want to test whether it is first order, then you're going to use that equation where you plot your ln 80 against time. That is, you're going to have concentration at time 1, concentration at time 2, concentration at time 3, and so on. Then when you plot that, then we're going to have example anyway, so don't worry. So we're just explaining the concept here. So that means you're going to have a straight line. If you plot ln 80 against time, if you have a straight line of this nature, then what that is saying is that this is a first order reaction. The same thing for second order. You can see, okay, why? So the same thing for second order. Now for second order, what you also do the same thing that we did for for zero and first order. Then you will also have your integrated rate equation. And if you plot the reciprocal of concentration at every time against time, if you get a straight line of this nature, that means that reaction is a second order reaction. Now, when you use any integrated rate law for a particular order, if you get a straight line, that means it belongs to that order. If you don't, that means it does not. It doesn't tell you which order it belongs to. It only tells you, does it belong to this order or not? Yes, no. If it doesn't belong to you, if it does not belong to that order, you need to go and use integrated rate law for order to figure out whether it belongs to that order or not. Now, this is the order of reaction, or this is the table for order of reaction. Now we have you can see the differential rate law for zero order. You can see the integrated rate equation derived from that integration, and you can see the kind of graph you must plot to be able to get that order of reaction. Now, there's something also called half-life expression. Okay, that means I'm still going to send you something on that half-life, but I need to explain. I don't know why I skipped it. So now the half-life of a reaction is the time it takes for the original concentration of your reactant to get to half. It's the time it takes for you to arrive at half the original concentration of your reactant. That is the half-life. Now, but of course, you can calculate the half-life for a reaction if you know the rate constant. So for each of this, and how do we we arrive at the half-life from the integrated equation expression. I'll do a slide and send it to you on half-life. Anyway, but again, it's here, so we just need to quickly explain it. So normally, like I said, it's the time it takes for your original for your concentration of your reactant to get to half of the original concentration. That means what we're saying is that if you're starting from 4 molar, what time does it take for that 4 molar to get to 2 molar? That is your half-life. If you're starting with 10 molar, what time does it take to get to 5 molar? That is your half-life. And half-life for every order of reaction is calculated from the integrated rate equation. How do you do that? You remember, we said, because your half-life is that time when your AT equals to A naught divided by 2. Remember, because that is going back to our definition. Our definition says the time it takes for your concentration to get to half of its original value. That is your half-life. We just said you're starting with 4. What time does it take to get to 2? So if you're starting with A naught, that means at half-life, your AT should be equal to A naught divided by 2. It means at half-life, your AT should be equal to A naught divided by 2. That's what I'm going to be writing in that slide. Okay, maybe I should just I can quickly write it on the board because we can do that. Let's quickly do that. So that I'm not just speaking. You can apply whatever I'm going to do to every other part. So so I'm going to take out. Okay, now I just want to stop that slide so that I can quickly use the whiteboard. Because I wasn't comfortable the way I was talking and there was nothing for you to look at. So that is the issue with physical chemistry. You want to write. Okay, so and again, we should always make sure that we can write anytime there's something so now, and what I'm saying is that remember that our integrated rate equation is equal to AT equals A naught minus KT. So that's our integrated rate equation. What I'm now saying is that when we're saying half-life, that means at half-life, our AT is going to be equal to A naught divided by 2. Because this is exactly, like I said, if you're starting with 4 molar, your half-life, because at this now, this is going to be TR. This is going to be TR. That means at half-life, your concentration gets to half of the original value, which is what you have here. So now, to now derive the formula for half-life, you just have to bring in, you substitute A naught divided by 2 for AT. You substitute A naught divided by 2 for AT. That means you rewrite that equation. And that equation is now going to be so that means your equation is now going to be, because remember you're coming from AT equals A naught minus KT. And that means you're now going to have A naught divided by 2 is equal to A naught minus KT. So meaning that ultimately you're now going to have, and remember you are looking for half-life. So, this is going to be T half now, which is your half-life. It's not just T, it has become T half because that is the designation for half-life. So, all you need to do is make T half the subject of the formula from this, and you'll arrive at, and of course, how do you do that? If you transfer this to this side and you transfer this to this side, that means you're going to end up with KT half equals A naught minus A naught divided by 2. That means at the end of the day, your T half now is going to be A naught divided by 2K from this. I don't have to write everything, but I want to believe that this is understandable for anyone who have what it takes to be in this class. Now, so I just wanted us to see how the calculation of half-life, or what I meant when I was talking about, because I was uncomfortable when I was talking and we were not looking at anything. So, okay. Now, so let's go back to our slide so we can continue, because we still have we already spent 30 minutes and we have to finish this morning. It's not like we have a choice. So now you have everything for first order, you can see for zero order, you can also see for second order. For half-life, you can do that calculation. Sorry, you can do the same thing for every order of reaction, and you arrive at that half-life. Now, the important part, the example, look at what we have here. The hydrolysis of ethyl benzoate by aqueous sodium hydroxide was followed at 25 degrees Celsius by titration of the sodium hydroxide against standard acid at different stages in the reaction. From the given data, show that the reaction is second order. The good thing here is they already told you, oh, this is a second order reaction, but we just want you to show us there's a second order reaction. Now you have time, you also have the volume of acid used. I'm sure you will be like, oh, okay, but they told us about concentration. Why are they writing volume here? There's no concentration here. Now, you see, if you look at that equation, this is where you also learning to read comes in, but it's not like we're going to explain, we'll still explain. But because I know that students kind of like do get confused a little bit here, which is still the reason why I like to use it as an example, because it kind of like tell you the kind of challenge you can actually face when you're trying to solve a problem in real time. So now if you look at this now, we have mu. And they're saying that hydrolysis of ethyl benzanoate by aqueous sodium hydroxide. And now, what they're now saying is that they are titrating, the titration that by titration of hydroxide against standard acid at different stages. Now, that means what they're monitoring is the concentration of the sodium hydroxide. In that reaction, you have ethyl nitrogen and nitrobenzoate. You also have sodium hydroxide. Those are the two reactants. But they are choosing sodium hydroxide to use to monitor that reaction. They are using sodium hydroxide, and they are titrating sodium hydroxide with HCl at every point in time. Remember, the higher the concentration of sodium hydroxide, the higher will be the volume of HCl used. And that is why this volume is directly proportional to concentration. So this volume can be treated as concentration of sodium hydroxide. This volume, because you see that the volume of the acid decreases with time. It's decreasing because as the reaction progresses, the concentration of sodium hydroxide also decreases with time. And they're just using that volume to test what is the concentration now. This is what is called a classical method in chemical kinetics, really. So they are using titration to monitor the concentration. Now, at the beginning, at time 0, it was 10 mil. That was the starting point. That is, they used 10 mil. Meaning that whatever concentration HCl had at the beginning was only, would take 10 mil of acid to be neutralized. At 95 seconds, it took 9.3. Meaning that at that particular point, the concentration has decreased and it can only take 9.3 mil now. And so on. So that volume of acid is proportional to the concentration of sodium hydroxide. We could have just written the concentration of sodium hydroxide there, but this question did not do that. And this is where reading and serious understanding comes in, really. And that is why I always decide to use it. Rather than writing this, we can just write the concentration of sodium hydroxide. But no, volume of acid, which is directly proportional to the concentration of sodium hydroxide, and it can be used. So now you have your data. This is your data. This is the concentration time data. I'm sure because you're seeing volume, it's still a concentration time data. And that is why I know that there are a lot of you that are not listening. I'll say this again. I'll still come back and ask, oh, okay, why did we have volume here? Now, you see, you could do this. I explained this using graphical method. So you can plot a graph. You can plot a graph of the reciprocal of concentration, that is the reciprocal of this volume against time. But okay, sorry, not the reciprocal of not the reciprocal of how will I put it now? So sorry, you can plot the reciprocal of that volume against time, which is the alternative method. A plot of the reciprocal of AT versus time will give you a straight line. You can do that. But another method of doing that, if you don't want to use a graphical method, is to calculate the rate constant. Now, because essentially, when you have a straight line, when you do that plot, remember, when you have a straight line, it is always said that the slope of that straight line is your rate constant. Now, and the rate constant must be constant throughout. If you do it for a reaction that is not a second order, you won't get a straight line. You will get a curve. And what does the curve mean? It means you will have different rate constants for the same reaction, which should not happen. Now, having the same rate constant, it means that you can take every data point and calculate the rate constant for every data point. Your rate constant for all the data points must be approximately equal. They must be similar when you do that. It's still telling you that if you plotted the graph, it will give you a straight line. And that is what is done here. For every data point, we calculated our rate constant using that equation. This is still the second order equation, but we just decided to make K2 the subject of the formula. When you do that, if you now look at all the rate constant that we have, you realize that they are approximately the same. That is telling you, if you use the graphical method, you still get a straight line. Now, okay, so this is where I brought the half-life. So, sorry, we already explained the half-life. I'm sure you know. So we already explained. I didn't know that it was even here when I was doing what I was doing. So, because I was wondering why it wasn't here. So, collision theory of reaction rate. Now, okay, that is for the order of reaction. Collision theory of reaction rate. Now, according to this theory, because we were talking about, for a reaction to take place, we spoke about rate, we spoke about everything, order of reaction. But what are those things that we have beneath that? What at the molecular level? What are those things that is going on that is responsible for everything that we just spoke about? According to this theory, a chemical reaction takes place only by collision between the reacting molecules. But not all collisions are effective. That is, if you have A reacting with B, all the molecules of A and all the molecules of B are going to be colliding. That is the only way you can have a reaction. But not all the collision that you have, that is, it doesn't mean that every time they collide, it must result in a reaction. No. The two main conditions for collision between reacting molecules to be productive. So that means there are conditions. It doesn't mean that every collision that immediately they collide, there's a reaction. There are conditions that must be fulfilled before collision can lead to a chemical reaction. The colliding molecule must possess sufficient kinetic energy to cause a reaction. That's one, sufficient kinetic energy. That is, they must also have proper orientation. So now, explanation of the above. That is, so the explanation, the reason why we have that is that there is a minimum energy necessary to cause a reaction to happen. If not, everything that gets in contact with each other will just be going into a reaction. But there is a minimum activation energy necessary to cause a reaction between colliding molecules. So only molecules that collide with kinetic energy enough to be able to surmount that energy barrier that will get into a reaction. So any molecule that is colliding with less kinetic energy, that means they are not going to be able to break that energy barrier and there won't be a reaction. That is why they must fulfill a minimum kinetic energy for them to go into a reaction. The second part, we talk about proper orientation. There is something called a favorable orientation, that is relative position at which a molecule must collide. Now, a good example, if you're talking about a molecule that is positively charged and a molecule that is negatively charged. Remember, even a molecule that is positively charged, there'll be some area, there'll be some angle of that molecule where there's going to be a surplus electron. But there's just going to be the broader area where it's electron deficient. You don't want, like, you now have two positive areas trying to collide with each other. There will be a repulsion between those positive areas. Or you have two negative areas, two electron-rich areas trying to collide with each other. Of course, there won't be a reaction. There will be repulsion. You only have a reaction when you have a positive area trying to electron deficient area, which is positive, and electron-rich area trying to collide with each other. That's when you have a reaction. That's a good example of what we mean when we're talking about good orientation for the reaction to take place. Now, and one of those things when we're talking about, when we just spoke about kinetic energy now, it means that the temperature has got is really important, because the kinetic energy more often than not will come from the temperature. So, and that's why temperature has got a significant effect on the rate of reaction. Now, it has been observed experimentally that increase in temperature leads to a remarkable increase in the rate of chemical reaction. And again, the rate constant. And again, the rate constant. Remember, we said that if you keep your temperature constant, your rate constant remain constant. But when you change your temperature, it has a very remarkable effect on your rate and also on your rate constant. Unlike concentration that changes, that we don't want, because more often than not, you can keep your temperature constant and determine your rate constant. So, but when you change your temperature, the rate constant also changes. Now, the relationship between, now remember we spoke about that energy barrier. It is because of that energy barrier that this idea of temperature becomes important. Now, and that's why there is a relationship between the energy barrier of a reaction, which is called the activation energy, and the rate constant, and even temperature. And that is it's that equation that you have there, which is K, Arrhenius factor exponential minus activation energy divided by RT. And the R is the gas constant, and T is the absolute temperature. So we can write that equation in this form also. And that means that you can determine, if you have your rate constant for a reaction at different temperature, you can determine the activation energy of that reaction by just plotting your log K against your, remember, at different temperature, you'll have different rate constant, because rate constant changes with temperature. So you can now plot your log K against the reciprocal of temperature. Then you can always get your activation energy from the slope of that graph, which is what you have here. Now, so this is an example for the decomposition of N2O5. The slope is minus 5,400. Hence, so let me give you so now, whatever slope you get is going to be equal to minus EA divided by 2.303 RT. So if you want to get your activation energy from that slope, you still need to make activation energy the subject of the formula. And of course, sorry, T is not going to be there. That's a mistake. The T shouldn't be part of, and please take note, T is not there. T shouldn't be part of that, because you're plotting your log K. T is not a constant, so it shouldn't be part of that equation. It's one of your variables that you're using in your graph. And your intercept is going to be your log A. So meaning this is an example of where there is a slope and you're trying to calculate the activation energy from the slope. So now again, you can also, so that's one way of determining your activation energy for a reaction. You can determine the activation energy if you know varieties of temperature and their corresponding rate constant. Again, if you just know two temperature and two rate constant, you know rate constant at two temperature, you can still determine the activation energy for that reaction. And of course, this is the formula. It's not coming from the same equation. This is the formula. Log K2 divided by K1 is equal to activation energy divided by 2.303 R and so on. So all you need to do is make the activation energy the subject of the formula and get out your value. So this is an example of that. So you have benzene diazonium chloride decomposes in the presence of water, according to the first order kinetics. If the rate constant at 25 degrees Celsius is 2.8 times 10 raised to the power 3 per minute, and the activation energy is 11.9 kilocal per mole, find the rate constant at 35 degrees Celsius. Now, in this case, you'll be given the activation energy. Yeah, you'll be given the activation energy, and you want to calculate the rate constant at one of the temperatures. You've been given the rate constant at a temperature, and you have to calculate the rate constant at another temperature. So by the time you do all this, you can see this is how it's done. Then you can get that rate constant. Now, of course, we already said that the catalyst does not alter the value of the equilibrium constant for any reversible reaction. Oh, sorry, forget this. What the catalyst does, like I said, it changes the pathway. What it does is that it changes the pathway. It doesn't do its own via pollution theory. It does its own. Its effect on rate of reaction is by changing the pathway completely. There's a difference between somebody trying to run from A to B and still move in, use a path, and somebody trying to get to A to B faster using another path. So there's a difference. The one that is still using the same line will have to run faster. The other one is not about running faster. It's not about running faster now. It's about using a shorter route. So what a catalyst does is take a shorter route rather than moving faster. So that is all we're going to do on chemical kinetics. So we want to move to chemical equilibrium. You'll ask all your questions together, because I know originally I wanted you to ask questions immediately after this, but I know that even if I did that, there will still be students who will still take me back to this chemical kinetics during the question and answer time. And I want us to even finish maybe so that we can ask something close to 20 minutes for question and answer. Okay, so let's go to chemical equilibria. So these are the things we want to talk about: reversible reaction, dynamic equilibrium, which are the last principle, factors affecting equilibrium position, equilibrium constant at constant pressure and constant calculation of equilibrium constant, relationship between equilibrium constant at constant pressure and constant temperature, temperature, then calculation of pH and solubility product. Now, so let's get to it. Now, there are some chemical reactions that they never go into completion. In fact, we always say that most chemical reactions don't go into completion, but proceed in both forward and backward direction. So, but there are some that appreciably you can't even expect them. Substantially, they don't go into completion at all. You can't even expect them to go into completion. So that means they proceed into both forward and backward direction. So such reactions are reactions we refer to as reversible reaction. Now, these are reactions that will be discussed under this topic. Give me a minute. I think I need to switch on the AC. I don't know why I'm this. Okay, sorry about that. Okay, so a reversible reaction is indicated as shown. So this is what you call a reversible reaction. You have the reactant and the number of molecules there. So A plus B give you C and D. Now, dynamic equilibrium. So now reversible reactions, they kind of like get into equilibrium under certain condition. So when you're starting a reaction where you only have your reactant, your A and B, so they're going to continue to form product at the beginning, because remember, you have zero product at the beginning. So, but now you get to a point, so the concentration of the product now continues to increase from zero, while that of the reactant continues to decrease. But now you now get to a point at which product this product now also try to dissociate and go back to reactant. It doesn't mean that immediately the reaction starts, you begin to have that. So now, so you get to a point where, okay, the product now starts dissociating, and they start going, because at the beginning, no product that will even dissociate anyway. But as you now begin to form the product, you now, the relative concentration of both determines the amount of products that now come back to reactant, and the reactants that still go ahead to form product. But now, so that means at every point in time now, immediately you begin to have appreciable amount of reactant, appreciable amount of product in your reaction mixture. Some of those products are forming reactants just as reactants are forming product. That will continue. So, but again, the concentration of the product will still continue to increase, because only a little, like I said, the relative concentration is important here. Only a little of the product forms the reactant at the beginning, because there's still a large amount of product. So, but you still, so as the reaction progresses, you still realize that while both forward and backward reaction are taking place, the concentration of reactant is still decreasing, while the concentration of the product is still increasing. But now you now get to a point where the rate of the forward reaction, or the rate at which the product are formed, and the rate at which product dissociate to form reactant, they are equal. They are equal. Now you have forward reaction, the rate of forward reaction equals the rate of backward reaction. Now, at that particular point in time, concentration of either side will not be increasing again. Concentration of either side will not be increasing again. And so now, when you now get to this point, equilibrium is reached when the rate at which reactants combine to form product equals the rate at which product dissociate to form reactant. Now, such equilibrium is what is known as the dynamic equilibrium. Now, the following are the features of dynamic equilibrium. Rate of backward reaction equals rate of forward reaction. Then again, reactants are randomly becoming product, and product constantly becoming product, and product constantly becoming reactant. You can only have this in a closed system. Why is a closed system important? We're saying a closed system because you're saying reactants giving product and product coming back to a reactant. If you are having a reaction in a situation where your products are leaving the system, then you can't have a product that will dissociate back to reactant. That is why a closed system is important, meaning that both reactant and product must be in a closed system. None must have a way of escaping. So that's what you are. Now, it does not mean that the concentration of the reactant equals the concentration of the product, because I realize that students always have this misconception. It does not mean that the concentration of the reactant equals the concentration of the product. No, that's not what this is saying. It's just saying that the rate of conversion of product to reactant to product are equal. Now, what are the factors that affect this, the equilibrium position? What are those factors that affect it? Because what do we mean even when we're saying that affect it? Because if we get here and we're like, oh, okay, so the concentration of both sides are static now, and that means the rate of forward reaction equals the rate of backward reaction. So now we have a dynamic equilibrium. You measure the concentration of it remains the same. The concentration of reactant is no longer changing. That of the product is no longer changing. What can you do to change that situation? That is what we mean when we say what are those factors that can actually affect equilibrium position. That is, you want to shift. You want that reaction to tilt towards a particular side again, rather than just staying static. You want the rate towards one side to increase. That's what we mean. And now that takes us to what is known as the Le Chatelier's principle, which says that if a constraint or a disturbance is placed on a system at equilibrium, the equilibrium position changes in order to cancel the effect of the disturbance. The disturbance in this context refers to a change in any of the factors that maintains equilibrium. Now, what is it saying? I just mentioned it now. You already have a reaction at equilibrium. Rate of forward reaction equals rate of backward reaction. Concentration of reactant constant, concentration of color constant. Now, that's a system at equilibrium. Now, you now disturb that reaction. Now, anything that can disturb it is a factor that can actually change the position. What do you mean by disturbance? Whatever you do that will tilt that in one direction or the other, again, remember, it's not tilting in any direction. It's balanced. Whatever you do that tilts it in one direction or the other, that's a disturbance. Now, what we're saying now is that, okay, so we already have a constant concentration of constant concentration of reactant and constant concentration of product. Now, all of a sudden, somebody just introduced more of the reactant into the system. That's a disturbance. That's a disturbance. Or somebody just changes. Remember, the rate of reaction also depends on temperature. Somebody just changes temperature. That's a disturbance. Or somebody changes pressure. That's a disturbance. Now, when you do that, remember there was a constant, because when we talk about that temperature, it's about the relative concentration of the reactant and product to each other. It must be of a particular value. That value is what is called the equilibrium constant. Whatever you do that now changes the concentration, remember, equilibrium, we will get to the formula. There's a way you calculate the equilibrium constant, and it depends on those concentrations. Now, you now introduce a concentration on one side, you now cheated on behalf of one side. Then the equilibrium constant must still remain the same. So the system will quickly convert some of those things you introduce into the system onto the other side so that the equilibrium constant can remain the same. And that is what Chatelier's principle is saying, that if a constraint or disturbance is placed on a system at equilibrium position changes in order to cancel the effect. You are introducing concentration, you are introducing temperature. The equilibrium will quickly change to be able to make sure that whatever it is you did is ultimately of no permanent effect, and of no permanent effect on the equilibrium constant, which should always. So now, the effect of temperature. So now there are three factors: temperature, pressure, and concentration. So when you how does a temperature affect equilibrium constant? But this is not just about any. You don't just look at reactions that okay, all reactions are equal or they are the same. No, they're not the same. How temperature affects equilibrium position depends on whether that reaction is exothermic or endothermic. And again, maybe better put, it depends on which side of the reaction is exothermic or endothermic. And I'm saying that because if the forward reaction for a particular reaction is exothermic, the backward reaction will be endothermic. This is an example. If N2O4 to give you 2NO2, so if it's endothermic, sorry, in this case now it is endothermic. Now the backward reaction will be exothermic. But now what do I mean by backward reaction? It means if you write it as 2NO2 to give you N2O4, that would be exothermic. Because this is endothermic, the backward, which is going to be N2O2 to give you N2O4, that would be exothermic. Now, but let's just look at this reaction now. This is an endothermic reaction. The forward reaction, that means it absorbs heat. It requires heat. Now, if you now try to increase temperature for this reaction, What that means is that the forward reaction will be favored. Because if you look at this, it's an endothermic reaction. It's a reaction that consumes heat, this forward reaction. The backward reaction will release it. The forward reaction consumes heat. You now increase the temperature. That means you're supplying more heat. So the consumption of heat direction is going to be favored, which is the production of more production of 2NO2. So when you increase the temperature, more 2NO2 will be produced, because that is what requires heat. But if you decrease the temperature, the backward reaction will be favored, because conversely, that requires reduction of heat. In fact, increasing heat works against that. So for this reaction, increase in temperature will favor the forward reaction, decrease in temperature will favor the backward reaction. And generally, increase in temperature favor the exothermic reaction, favor the endothermic reaction, while decrease in temperature favors the exothermic reaction. Now we go to pressure. Effect of pressure is applicable only to gaseous system. And I already said that, I think, in the course of our chemical kinetics conversation. Most of the time when we talk about pressure, you can't be talking about solids and you think pressure is important. No, more often than not, they're about gases, really. So in order to understand the effect of pressure, the total number of moles of the reactants, they're very important. So just like whether the reaction is endothermic or exothermic is important for temperature, the number of moles of reactant relative to that of the product is important for pressure. So, and we know that the higher the number of moles, the higher the pressure. We know the higher the number of moles of gases, the higher the pressure. So that means that whichever one has higher number of moles is actually exerting more pressure than the one with less number of moles. Now, in this reaction now, where you have 4 moles of reactant and 2 moles of product, what it implies is that the reactants is actually exerting more pressure than the product. So now, when you now increase the pressure, what it means that the equilibrium will shift more to the right, because that is what is exerting more pressure on the system. So when you increase pressure, the equilibrium shifts to the right. When you increase pressure, the equilibrium favors the side that's exerting less pressure. So an increase in pressure changes the equilibrium to the right to favor the species that exert less pressure. So when you decrease pressure, the equilibrium will favor the side that's exerting the less pressure. And you determine the amount of pressure they exert relative to each other by looking at the number of moles of those gases relative to each other. So in this case now, if you increase pressure, more ammonia will be produced if you decrease pressure. And why is that? Because ammonia was exerting less pressure originally. So that means more of it will now be produced to balance that pressure effect. So, but if you decrease pressure, then more nitrogen and hydrogen will be produced. Now, effect of concentration. Now, for a reaction at equilibrium, the forward reaction is to be favored. Now, when you're talking about equilibrium, effect of concentration on equilibrium, at the end of the day, it's like in this case, it's absolute. You're not looking at, in temperature, you look whether it's reaction is exothermic or endothermic. In pressure, you look at which one has higher number of moles of the gases and higher number of moles of reactant and product. And but for concentration, no. There's actually no specific thing to look out for. There's just a general rule for concentration. Whichever side you are adding to, if you're increasing the concentration of the reactant, more products will be produced. If you're increasing the concentration of the product, more reactant will be produced, which makes sense, really. Because remember, the relative concentration is what determines the equilibrium constant. Now, that constant must remain constant. If you introduce more to one side, some of that more you introduce will go back to the other side, so that's to make sure that that constant still remains the same. So when you even take away, when you reduce concentration on one side, then some that is the other side now will come back and replace what you removed, so that that constant can still remain the same. So now, the equilibrium constant, how do we? So equilibrium constant. So now, the concept of equilibrium, so you can understand that by just looking at our original reaction. But again, we already said that at equilibrium, the rate of forward reaction will be equal to the rate of backward reaction. So if you apply the law of mass action, you write it this way. And again, please, what you just need, remember I told you that when reactions are elementary, the molecularity and order of reaction seems to be, they are the same. So we're trying to, that's the assumption here. And that, so we're dealing with elementary reaction here. Essentially, that is the assumption here that, okay, we're dealing with elementary reactions. Whether the order are different or not are not important here. And that's why you can actually have your R1 equals to this, your R2 equals to, because this is how to, from our chemical kinetics, you already know how to write rate of reaction. And now, so that we can quickly deal with what I said, that molecularity is not the same thing as order, but for elementary reaction, they are, and that's what we have there. Now, the law of mass action states that the rate of reaction is directly proportional to the concentration of reactant. So, meaning that if you equate R1 to R2, then you're going to end up with equation 6, and you can rearrange equation 6 to give you equation 7. And of course, at that now, that is your equilibrium constant, because your K1 divided by K2 is equal to equilibrium constant. So, but again, now, talking about the unit of equilibrium constant, the unit of equilibrium constant depends on whether you're calculating Kc, that is, you're calculating your equilibrium constant from concentration, or either you are calculating it from pressure, and even the number of moles of the individual reactants that are involved. That is what determines your equilibrium constant. And a good example for that reaction, if we want to calculate the equilibrium constant for it using the concentration, you can see what the unit will be. Raised to power 2. You can see the mole per dm cube raised to power 2. What I'm demonstrating here is that equilibrium constant will depend on, the unit of equilibrium constant will depend on, are you calculating Kc, which is equilibrium constant from concentration, or Kp, equilibrium constant from pressure? And again, what are the number of moles? Because you can see that for ammonia, where you have 2 molecules of ammonia, is raised to the power of 2. Nitrogen, 1 molecule raised to the power of 1. Hydrogen, 3 molecules raised to the power of 3. So that's how you calculate the concentration. And again, for pressure, you're no longer using mole per dm cube. Now you're using atmosphere for pressure. So that's why I said it depends on what the parameters you use to calculate and the nature of that reaction itself. So, and you have an example for that ammonia formation. For Kc, you have the unit. For Kp, you also have the unit. And just as okay, the unit for Kp can be in atmosphere. It can also, because remember that for pressure has varieties of unit also. So it depends on what unit you're also using. So that's also another one, which is also gaseous. So the denominator, 2 molecule, the numerator, 1 molecule, meaning that, of course, you're going to have 2 units divided by the one that has 1. So you end up with atmosphere. The unit of Kp is now going to be atmosphere raised to power 2, because your reactant is 2NO2, divided by atmosphere, because because your product is 2NO2, divided by atmosphere, because your reactant is 1 molecule of N2O4, and that gives the unit atmosphere. So you can see that there's actually nothing like a static unit for equilibrium constant, which is exactly what I'm driving at. Now, so this is an example also. So this is an example of how to calculate that, because remember, H2O is 1. Why is H2O 1? H2O1 is 1 because in this reaction, the concentration of H2O is not going to be changing. Its water is going to be in excess. It's not going to be changing at all. And because its concentration is not changing, it's seriously of no effect to this reaction. And that's why it's going to be 1. And what you use are just going to be the other reactant. Now, let's now look at varieties of examples of how to calculate equilibrium constant. So now you have 1 mole of iodine and 1 mole of hydrogen. I'll just take in a place. Sorry about that, please. Okay, now 1 mole of iodine and 1 mole of hydrogen are mixed and allowed to reach equilibrium at 1 atmosphere. The amount of hydrogen iodide present at equilibrium is 1.5 mole. Calculate the equilibrium constant, Kp at 300 Kelvin. Now, that is the equation for that reaction. And I would want us to go through this patiently because I don't want, because this is part of the reasons why I decided to use 2 hours for this class. So now, 1 mole of iodine and 1 mole of hydrogen are mixed and allowed to reach equilibrium at 1 atmosphere. Now, the 1 atmosphere set aside first, but the most important thing is that you have 1 mole of, the most important thing is that, okay, you have 1 mole of hydrogen. You can see the initial amount, 1 mole of hydrogen, 1 mole of iodine. And at the beginning, 0 mole of hydrogen iodide before the commencement of the reaction. Now says that the amount of hydrogen iodide present at equilibrium is 1.5 mole. Now, so at equilibrium, we already know that we have 1.5 mole of hydrogen iodide. Now, that tells us the amount of hydrogen and iodine that has reacted. If you look at the mole ratio, it is 1 to 2, meaning that for every 2 mole of hydrogen iodide produced, 1 mole of hydrogen is consumed, 1 mole of iodine is consumed. That means that for 1.5 mole of hydrogen iodide produced, 0.5 mole of iodine is consumed and 0.5 mole of hydrogen is consumed. And that's why you see negative, negative. That means those are reactants consumed, and you see positive, meaning hydrogen iodide produced. Now, so if 0.75, because what we're interested in is actually not really what we're consumed. We want to know what is present at equilibrium. That's what we need. We want to know what amount is present at equilibrium. That is why 1.5 for hydrogen iodide is important, but 0.75 and 0.75 for hydrogen and iodine, they are just means to end for us. They are not what we need. We just need to use them to get what we need. What we need is what is left, not what was consumed. So, because you're going to be calculating your equilibrium constant using what is left, not what was consumed. So, which is why now we can now calculate what is left from what was consumed. So 0.5 consumed, that means from 1, that means we are left with 0.25. 0.25. Now, the total number of mole at equilibrium. Why is this important? Because we're going to be using pressure, because we're using pressure. And at the end of the day, the mole fraction, there's something called mole, if you want to calculate the pressure exerted by a gas, Because as you have all these gases, the three of them, they're exerting pressure. Now we want to know what pressure does each of these gas contribute. And to be able to know that, we need to know the mole ratio for every gas. We need to know the mole ratio for every gas. I'm sure that I've forgotten the lecturer who taught you this as part of what you, okay, is it, sorry, I think you're already doing that in second semester, I guess. So the partial pressure exerted by every gas is going to be the mole ratio of that gas multiplied by the pressure, multiplied by the total pressure. Because if you look at the question, says the pressure is allowed to reach equilibrium at 1 atmosphere. The total pressure is 1 atmosphere. But we want to know what pressure is exerted by each of these gas. And we can only know the pressure from their mole ratio. Now, and that is why we're adding together all this number of moles, so that you don't know why we're adding together all the number of moles. We're adding the number of moles together so that we can know the mole, the fraction of that number of mole that belongs to each of the component. So in this case now, if the total mole is 2, because 0.25, 0.25 plus 1.5, that gives us 2. If we now want to know the mole fractions of hydrogen, hydrogen is its own number of moles is 0.25. We now divide that 0.25 by 2 to get the mole fraction. Now it is 0.125. Now the partial pressure exerted by hydrogen will now be that mole ratio multiplied by the total pressure. The total pressure is 1, the mole ratio is 0.125. And that is why we did that. And eventually we get 0.125 atmosphere as the partial pressure exerted by hydrogen. We do the same thing for iodine. We do the same thing for hydrogen iodide. So at the end of the day, now we know, because remember, you want to calculate your pressure, and you need the partial pressure of each of them to calculate your equilibrium constant. Now, it is those pressure that we have for the individual, because the question did not give us the pressure exerted by each of the gases. We were to find that ourselves, and that's how we arrived at those individual pressure that you can now use to calculate your equilibrium constant. Now, in this case, now you just substitute those partial pressure and you get equilibrium constant of 36. And of course, there's no unit here because you have atmosphere square divided by atmosphere square, so no unit. Another example, phosphorus pentachloride dissociate at high temperature. The system reaches equilibrium at certain temperature when 95%, this is presenting the same in another for when 95% of a sample of PC5 has dissociated. The total equilibrium pressure is 2 atmosphere. Calculate the value of Kp. It's still the same, but presented in a different way. So your reactant, you're starting with 1 mole of your reactant, so 0 mole of the product. You're now saying that you have 35%. That the 35% of your sample dissociated. So when the 95% of the sample, and it's 1:1, the reactant and product is 1:1 here. 1 mole of PCl5 will dissociate to give you 1 mole of PCl3 and 1 mole of PCl2. So that means when you consume 0.39 mole of PCl5, you will produce 0.39 mole of PCl3 and 0.39 mole of Cl2. But like I said earlier, what we're interested in is not what was consumed, it is what is left. That's what we need. And eventually we now, just like we did the other time, we now calculate what is left from what was consumed, really. So, because remember, the 0.39, 0.3 are still there because remember, those are products. That's what is left. But for the reactant, you need to subtract now. And so don't confuse this, because remember that for the first reaction, we were given the amount of the product. But in this case, we were given the amount of the reactant consumed. But at the end of the day, the arithmetic manipulation is still the same thing. So at the end of the day, you have the number of moles for left in that reaction medium. So we go around and do the same thing because we just want to calculate the pressure exerted by each of this. But now the difference is this. The other one was 1 atmosphere. That is the pressure, the total pressure. In this case, total pressure is 2 atmosphere. So that you can calculate your mole fraction. And after calculating your mole fraction, you can now go ahead and calculate your partial pressure for each of the gases. When you get your partial pressure, you can now calculate your equilibrium constant. Okay, another question. I hope I finish, so because I want us to have 20 minutes for question and answer. So I have 17 minutes left. If we're going to have, okay, 16 minutes left if you're going to have that. So, and I do not want to rush anyway. So now, the next question says 1 mole of ethanol and 1 mole of ethanoic acid were mixed and allowed to reach equilibrium at 25 degrees Celsius. Now, the amount of ethyl ethanoate in the equilibrium mixture was found to be twice the amount of ethanol. Calculate the equilibrium constant. Okay, I think I need to take that question again. 1 mole of ethanol and 1 mole of ethanoic acid were mixed and allowed to reach equilibrium at 25 degrees Celsius. The amount of ethyl ethanoate in the equilibrium mixture was found to be twice the amount of ethanol. Calculate the equilibrium constant Kc for the reaction at 25 degrees Celsius. In this case, now we're using concentration, no longer pressure. So now this is the equation, and we're trying to lay out those information. You can see 1 mole of ethanol, 1 mole of ethanoic acid. At the beginning, 0 mole of ethyl ethanoate and 0 mole of water. Now, how do they change? So let us use X to represent the amount of mole produced. To represent the amount of mole produced, meaning that X mole of ethyl ethanoate is produced, and it's 1:1. It's 1:1. When you produce 1 mole of ethyl ethanoate, that means you must have consumed 1 mole of ethanol, 1 mole of ethanoic acid, then you produce 1 mole of water. It's the same thing here. When you consume X mole of, when you produce X mole of ethanoic acid, ethyl ethanoate, that means you have consumed X mole of ethanol and X mole of ethanoic acid and X mole of water. Now, what is left? Like I said, it's not what has been consumed that is important, it is what is left. We know now that you have X mole of ethyl ethanoate and X mole of water left, but what is left for the reactant? We still need to calculate that, because the only thing we know about the reactant up to this point is what was consumed. Now, to calculate what is left, since the initial amount was 1 mole, so that means we're going to subtract what is consumed from the original value to get what is left. 1 is the original value, X was consumed, and that's why you have the equilibrium amount for ethanol to be 1 minus X, and the same thing for ethanoic acid, 1 minus X mole. Now, and remember, the question also says that the amount of ethyl ethanoate in the equilibrium mixture was found to be twice the amount of ethanol. Now, what that is saying is that the amount of ethyl ethanoate is X, but they're saying that it is twice the amount of ethanol. That means X is going to be, and the amount of ethanol is 1X. So that means X is going to be 2 brackets 1 minus X. That is putting that information into a mathematical form here, because it's very important, because that is where, because our X is what is going to tell us everything here. So that is how we get our X. So you now make your X the subject of the formula from that equation. You get 0.33 mole. Now, you can now calculate your equilibrium, now that you know your X, and we already have the value for equilibrium amount, though not in the absolute term. So now we can now have the value for the equilibrium amount. So meaning that if X is equal to 0. Hold on. Something seems off there. Oh, okay, sorry, it's correct. It's correct, because if our X sorry, something is wrong here. I think I made a mistake when I was doing this. Because our X is equal to 0.33. So now, you see, the 0.33 that we have here, I think should be what we have for X. And 0.67, hold on. So this should be something is not right there. Sorry, I'll get back to this. I don't want us to, because we don't have much time. I'll get back to this, resolve it, and get back to you on this. But something seems wrong there. X, because this is X. So this should be 0.33. Okay. I think there is actually nothing wrong. It's about, that just appear to be it looks like a contradiction, because we're just giving effect to the amount of ethyl ethanol in the equilibrium mixture was found to be twice the amount of ethanol. So at the end of the day, when we have our X to be 0.33 and the amount of ethyl ethanol must still be double the amount of ethanol, so we get 0.67, because it's going to be 0.33 multiplied by 2 now to give you 0.67. But again, I still need to, I'm going to take a second look at that solution to that equation and see what's going on. But because I don't want us to be why we won't finish on time. So now, relationship between Kc and Kp. So now, there's a relationship. Remember, there's a equilibrium constant that you can calculate from concentration. You can also calculate from pressure. For equilibrium reaction of this type, so Kc is related to Kp by this equation. That is, Kc is going to be equal to Kp. We're not doing any derivation here. Kc is just equal to Kp RT raised to power A plus B minus C plus D. That is the change in number of moles between reactants and the product, and that's written as delta N, where R is the molar gas constant and T is the temperature. So you can now calculate Kc for the reaction in example 2. Which one is example 2? So it's talking about Kc for this reaction in example 2, and because we already have pressure Kp to be 0.36. So it's 0.36 atmosphere. That is for Kp, and you already have your gas constant given, and the temperature is 60 degrees, and this is absolute temperature. You convert that 60 degree to Kelvin. So when you convert it to Kelvin, and the change in the number of mole, meaning that this is going to be A plus B, which is 1 minus C plus D, which is 2, because you have 1 molecule of reactant and 2 molecules of product. So that means that is going to be -1. And so that gives you your Kc. So that is that. Then the calculation of pH and pOH. So for that, the formula for the calculation of pH is minus log H. And of course, which is still the same thing as the minus log of the oxonium ion, which is H3O plus. So your pOH is going to be minus log of hydroxyl ion. So for any material, your pOH and pH, if you add them together, they must be equal to 14. Now, for a strong monoprotic acid, that is, you're talking about an acid. So you're saying that the concentration of the acid is going to be equal to the concentration of the hydrogen ion. That is the difference between an acid that dissociates completely and one that does not dissociate completely. So when they dissociate completely, if I tell you I have 0.1 molar acid, you already know that If it is monoprotic, I'm going to have 0.1 molar hydrogen ion also. Now, so if I want to calculate the pH for that, I can take the concentration of my acid to be the concentration of the hydrogen ion. So calculate the pH for 0.01 mole per dm cube of hydrochloric acid. So just a minute. Okay. Something wiggly occurred to me. I just needed to check. Okay. Now, so that means all you need to do, because what this is saying is that it's just 1:1. So the concentration of the acid equals the concentration of the hydrogen ion. So you can just substitute the concentration of the acid for the concentration of the hydrogen ion, and you get your pH. In this case now, so since the concentration of the acid is 0.01, so your pH is going to be minus log 0.01, and that gives you 2. If it was diprotic, that means for every monoprotic means for every molecule you have 1 hydrogen ion. Diprotic, for every molecule you have 2 hydrogen ion. So, but for diprotic, that means for every acid you have 2 hydrogen ion. So that means for every 1 mole of acid you will have 2 mole of hydrogen ion. And that is why when you're calculating for a diprotic, a strong diprotic acid, now strong diprotic acid, that's important because that means they undergo complete dissociation. So that is why we're saying strong. Now, so when you now have a strong diprotic acid, that means you're going to multiply the concentration of your acid by 2 to get the concentration of your hydrogen ion. A good example is H2SO4. For every molecule of H2SO4, you have 2 molecules of hydrogen ion. That means when you have 1 mole of H2SO4, you're going to have 2 mole of hydrogen ion. And that is why to get your pH is going to be minus log 2 multiplied by the concentration of the ion, which is why in this case, the concentration of the ion is 0.0068. So the concentration of the acid is 0.0068. That means the concentration of the hydrogen ion is going to be 0.0068 multiplied by 2. So now you calculate your pH from that. And that's why you have your pH to be minus log of 0.0136, which is as a result of the multiplication of 0.0068 by 2. Now for weak acid, weak acid is an acid that dissociates partially in solution. That means they do not undergo complete dissociation. And in this case, that means the concentration of the acid is not equal to the concentration of the hydrogen ion. Now, the dissociation of the acid can be defined by their equilibrium constant. That is to be able to calculate the amount of hydrogen ion you have for every mole of that acid. You must know their extent of dissociation. And that extent of dissociation is given to you. And this is important because you can't have the hydrogen ion without the dissociation of the acid. And the more they dissociate, the more hydrogen ion you have. And that's why if somebody tells you for a strong acid, I have 1 mole, you will know the number of hydrogen ion you have as long as you know whether the acid is diprotic or monoprotic, because you know there's going to be complete dissociation. But for weak acid, that doesn't give you that information because there's no complete dissociation. You need to know the extent of the dissociation. And dissociation constant tells you that extent of dissociation. So unlike the strong acid, where all you need is just the concentration and whether they are diprotic or monoprotic. For weak acid, you need an additional information, which is the dissociation constant, because you need to know the extent of dissociation. So now let's now look at this. So let us consider, so let the acid be represented with HA, whose dissociation is this, and we're saying that it's not dissociating completely. So let the concentration of the acid be Y mole per dm cube. Assume the volume of the acid is 1.0 dm cube. And the X mole of the acid dissociate. The following concentration can be estimated for the species at the initial state. We're saying that at the beginning, we are having Y mole. That's what we say. Y mole of the undissociated acid. At the beginning, 0 mole of hydrogen ion, 0 mole of the anion also. Now, change in concentration, we're saying that, we already said that the volume of the acid is an X mole of the acid dissociates. We're saying that out of that X mole dissociate. And since it's 1:1, when X mole dissociate, it's going to give you X mole of the hydrogen ion and X mole of the A minus. At equilibrium, what do we have? We already said it that what got consumed is not important. It is what is left at equilibrium that is important. At equilibrium, that means out of Y, X has been dissociated. So what is left is going to be Y minus X for HA, and X is going to be left for hydrogen ion, and X for the A minus also. And of course, for the water, since we say that, okay, this is a constant concentration, it's an excess, so we're not even relating with it at all. So changing concentration, that means raise it to a power of 0, then that gives you 1. So it disappears completely from the equation. So that ultimately now, you can now substitute for your equilibrium constant. That means it's going to give you X squared divided by Y minus X. But Y is far greater than X because we're saying that it is a weak acid. That means that the dissociation is very weak, meaning that what is consumed is going to be far less than what, because we said that X mole of the acid dissociates. But because it's a weak acid, and remember, weak acid have very weak dissociation. So what that is telling us is that what is going to be dissociating is going to be very small. And that's why Y is far greater than X, since we're dealing with a weak acid. So if we now do that, what does that mean? That means our Y minus X is now can be approximately be equal to Y, meaning that our Ka now can be equal to X squared divided by Y. Now, meaning that our X can now be root of Y multiplied by Ka. And remember, our X from this equation is our concentration of the hydrogen ion. Meaning that at the end of the day, when you want to calculate pH for a weak acid, you don't just need its concentration, which is Y, the kind that we needed for the strong acid. You need its concentration. You also need the dissociation constant. And your pH is going to be the minus log of the root of the concentration multiplied by the dissociation constant. So now you have an example. Calculate the pH of 1.0 times 10 to the power minus 2 mole per dm cube of ethanoic acid, which has a dissociation constant of 1.76 times 10 raised to the power minus 5. In this case, now you already have the concentration. You also have the dissociation constant. So, and according to what we said, of course, you're just going to be multiplying. You're going to be, because remember, our X, we know what our X is. So if you want to do our X, you're going to be multiplying these two together, and you get their root. And their root is going to be our hydrogen. It's going to be our hydrogen ion concentration. So, and that's what is done here. Our hydrogen ion concentration is what you have here. You multiply the two, you calculate their root. And now, that's our hydrogen ion concentration. And you now find the log of that value to give you that information. Now, strong base. This is also similar to what we're doing. But again, when you calculate the pH, so the pH for a base is actually minus the log of hydroxyl ion, while now the pH of that same material, you are going to subtract the log or the pOH from 14 to give you. Remember, we already said pH plus pOH must be equal to 14. So if you know the pOH, you should be able to calculate the pH. So if you want to calculate the pH for an alkali or a base, then that means you first calculate the pOH, then you can now get your pH from that. So now, calculate the pH of 1.0 times 10 to the power minus 2 mole per dm cube of sodium hydroxide. Hydroxyl, we already know the concentration. This is a strong acid also. So when we do our pOH, so that means that's going to be minus log of 1.00 times 10 to the power minus 2. So that gives us 2. To get the pH, we subtract that 2 from pOH. Sorry, from 14, sorry. to give us the pH. Now, so the last topic is going to be the solubility product. I thought I was going to. Okay, so but we don't have a choice. We really have to do this. Now, so the concept of the solubility is just like we're talking about the dissociation constant for acid now, that, okay, when they do not dissociate completely, the same thing happens in this case, a similar thing, happens in this case, because we're talking about salts that are not very soluble, that they're only slightly soluble. For instance, if given amount of silver chloride, if a given amount of silver chloride is added to a known volume of water, it dissolves until the solution becomes saturated and you will no longer have any solution. Now, equilibrium is then established between the salt and its aqueous solution, because you're going to have some salt, you're also going to have some the dissociated salt also. They're also going to be part of it. The aqueous ions are also going to be there. Now, and that's why, but of course, we're not putting water here because of what we said about water. In this case, of course, you're going to have them in excess. Nothing is happening to their concentration. So we're not even going to be bringing them into the equation. They have constant concentration. Raised to power 0, they equals 1, so we don't need that. And that's why we're not even talking about water here. It's part of the fact that we're talking about solubility. So K equilibrium, which is, now you now write this for equilibrium. Now, in this case also, because we're talking about sparingly soluble salt now, we say, oh, okay, it's insoluble, meaning that only very little, for solubility product, only very, very little of this actually goes into the solution. So you're still going to represent this as 1. Your AgCl, that is your salt, your solid salt, is still going to be 1. Because the solid salt, you can't be talking about concentration of solid salt, because we can just assume that you're talking about a constant or a changing concentration for a solid salt. So, which is still why they're still raised to power 0, and they're still going to be equal to 1 in that equation. And that is the formula for your solubility product. So that means for any salt you want to write solubility product for, and you have examples, this is how you write your solubility. This is how you write your solubility product. And take note also for something like BaCl2. So you can see that the 2 is actually raised to the Cl is raised to the power of 2. And the iodine is also raised. So normally the number of mole, you raise it to the power of the number of mole in your equation. So now calculation involving KSP. So calculate KSP for 0.002 mole per dm³ solution of barium chloride at 25 degrees Celsius. So now we already know what we do, because we're saying that you have 0.002. And for this now, for barium, for every mole of BaCl2, you have 1 mole of barium. For every mole of BaCl2, you have 2 mole of sodium chloride. That is very important. And that means that in this case now, the concentration of barium in BaCl2 is going to be 0.002. While for chloride, it's going to be multiplied by 2. Before, for every mole, you have 2 mole of CO2, you have 2 mole of chlorine. And that's why you have to multiply that by 2. So at the end of the day now, you now do your calculation. But again, in spite of the fact that you multiply by 2, you're still going to raise it to the power of 2. Anyway, because that is the way the formula works. So that gives you your KSP for that. Then you do the same thing also. It's the same thing for silver chromate. Now, what do you use solubility product for? You can also use it for the calculation of solubility. Hold on. For the calculation of solubility. Remember that when you talk about concentration, when you calculate KSP when you talk about this concentration of that salt, you're essentially talking about the solubility of that salt also. So, which is why if you know the KSP, you can calculate the solubility, which is going to be manipulated as concentration. Or if you know the concentration, you can calculate the KSP. And that's why solubility is defined as the number of moles of the solute that dissolves in 1 dm³ of the solution. So the solubility also can be calculated by expressing the concentration of any of the constituent ions in terms of their KSP, taking into consideration the mole ratio of the ions. So it's the same thing that we did up there, that you just have to reverse here. And it's just all about changing whatever is the subject of the formula. And you're going to still get the same answer. So that's where I want to stop. So now I want questions on everything we did today and even from yesterday. Okay, so we have 12 minutes. So we can now go back to our question and answer. And I need to say this, your question is going to be, your test is going to be online. And we're going to be using, okay, don't worry about that. You know what we're going to use eventually, but just get your internet and everything ready. And again, please, I'm going to still post this. Make sure, I don't want to hear story of, sorry, my internet was bad, I couldn't submit. You'll be given the specific time, and immediately that time is up. If you do not submit, that's your problem. Because go and ask, you see, these questions, these complaints of internet, I use internet. I've got about 3 varieties of, because I don't want any problem with internet. So I've got varieties of because I know that my work depends on it. If your study and your test depends on it, then, because we live in an age where we do a lot of things online now, so it's something you should be prepared for. It's 40 questions to be answered in 40 minutes. And we're doing it in the evening on Thursday because we want to make sure that everybody is done with, you're not stuck where you're doing, and that's why we put it at 5, where you're doing your GST. We don't want that to stand in the way. And we push it to Thursday because everything we've taught is going to be taken into consideration. That is why we push it to Thursday. We don't want to, and that's why we're not doing it on Monday, we're not doing it on Tuesday, we want it on Thursday. So for me, and I think that is still okay. So your question now, so let's start taking questions. So please raise up your hand if you have questions. Allow Emmanuel. So mute, please.
Sir, why are we not receiving slide again?
I already sent slide to you now. I sent a slide to you yesterday. I'll send this today. I sent one yesterday to your class rep, to your Telegram platform.
Oh, okay, sir.
Why won't I must send slide. So I did that, and I'll send this today again.
Okay, thank you, sir.
All right. Question, please. All right, so I want to assume there are no questions. So good morning, everyone. So I'll see you during the test.